Hello and welcome back. In section 5.5, we work with the fundamental theorem of calculus. So first, our definition. F is continuous on closed interval AB, and cap F is any antiderivative of F and the integral from point A to point B of f of x times dx is for cap f of b minus cap f of a. So since cap f can be any antiderivative, we're going to let c equal 0 on our definite integrals. Since we can pick any, we can have our plus c be worth pi/19, but 0 is easier. So generally we would work with 0. So I like to start with an example where I can convince you geometrically that this is in fact correct. So let's consider f of x is worth the sum of x and 2. We'll find the area under f of x from x is 3 to x is 6. So option 1 is geometric. So f of x is x plus 2 is just a line, slope of 1, y-intercept at 0, 2. And we're looking from x is 3 to x is 6. Now this is not necessarily drawn to scale. So some ordered pairs on here, 3, 0, 6, 0. F of 3 is 5. And f of 6 would give you an 8. Now, if you have the formula for the area of a trapezoid memorized, that's great, and you can use that. Since most of you likely don't have that memorized, what I like to do is just cut it into a triangle and a rectangle. A little bit easier to do. So this ordered pair would be at 6, 5. So our area would be the area of the rectangle. Well, this is 3 units wide and 5 units tall. So 15 square units plus half of the base times the height for the rectangle. The base is, again, 3 units. And our height from 5 to 8 is also 3 units. So A is 15, which is 30 halves, plus 9 halves, 39 halves square units. So let's see that this also gives us the same result. So f is definitely continuous. In this case, f is a polynomial, so it's continuous everywhere. So this is saying that the integral from a to b, so from 3 to 6, of x plus 2 times dx should be cap f of a minus cap f of b minus cap f of a. So first we'll do our antiderivative. Antiderivative of x. Our exponent was a 1, now it's a 2, so we'll need a 1/2. Antiderivative of a constant is a linear. And we evaluate these from x is 3 to x is 6. And this should give us the same end result. So we have half of 36 plus 12, so plugging in the 6, minus half of 9 plus 6. So we have 30 minus 9 halves plus 12 halves. So we have 60 halves. And then we have minus 21 halves. And there's our 39 halves square units. So we do get the same solution out of this. So this is how we find the area. So one little note, the reason that we were allowed to choose our C, if you notice here, when we do our subtraction, even if I had the same plus C attached to both, C minus C is 0. They would cancel out no matter what antiderivative we chose. That's why we chose C to be 0 for the definite integral. So the next one, we wouldn't be able to do a geometric interpretation. We could do approximations using Riemann sums, but we don't have just a simple formula for this without calculus. So we're going to find the area under f of x is x squared minus 2x plus 5, and the interval -3, 4. So these are x values. So if you want for emphasis, you can say x is on the closed interval 3, 4. So a quick rough sketch. We have our vertex in Q1. You can just kind of complete the square mentally to figure that out. Half of -2 is -1, square that is +1. So we can add and subtract 1, so y is x minus 1 quantity squared plus 4. So we have our vertex up there at 1, 4. So again, f is continuous everywhere since it's a polynomial, and we're looking from -3 to +4. So on 3 sides we have nice neat line segments, but on that 4th side we have a curve. So that's where we would need calculus for this. So from -3 to +4, integral of x squared minus 2x plus 5, close it up, times dx. So this will give us our area underneath the curve, that little red section that I shaded there. So antiderivative of x squared, exponent was 2, now it's a 3, so I'll need a 1/3. Hang on to the -2. X was to the first, now it's to the second, I'll need a 1/2. 5 is now 5x, and we're evaluating from So that's what the straight line means, evaluating from x is -3 to x is +4. So then that's 64 thirds minus, this is just a 1 here. 2 1/2 is a 1, so minus 16 plus 20 minus, so 3 cubed 27, so -27 thirds is -9, minus -3 squared is 9, and then minus 15. So plug and chug on there, and we're at 175 thirds. So 58 1/3 square units. So again, this one, we wouldn't have a simple way to do that using just rectangles and triangles anymore. We could approximate it using them, but we wouldn't get an exact value out of those. All right, so I'm gonna have you all try one out. So we're gonna find the area under f of x is 3 root x plus 1. X is 1, 2, x is 9. So the area under that curve. So make a quick sketch and go ahead and find the area. Okay, welcome back. So your quick sketch. This is based off of the square root function. We have stretched it by a factor of 3 vertically and slid everything up 1. So we have basically this kind of shape going on. And we're looking from 1 to 9. So our area would be the integral from 1 to 9 of 3x to the 1/2 plus 1 quantity times dx. So notice here we went from radical notation to exponent notation to make the calculus a little bit easier. So we'll do the antiderivative. X to the 1/2 is now x to the 3/2, so add 1 to your exponent, and I'll need a 2/3 there. Integral of 1 is 1x, and we're looking from x is 1 to x is 9, and a little bit of simplifying there. So this is 2x to the 3/2 plus x, evaluated from x is 1 to x is 9. So 9 to the 3/2 power, 2 in the denominator means it's square root. Square root of 9 is 3. 3 cubed is 27. 27 by 2 is 54. 1 to any power is 1. 1 times 2 is 2. 2 plus 1 is 3. So 63 minus 3, so 60 square units. So we ended up with a nice clean integer solution on that one. All right, so next up, we look at 2 different methods to do definite integrals using substitution. So option 1, we're going to look at the integral from 1 to 5 of x squared over the quantity x cubed plus 5, all of that times dx. So either way, we're going to need a little bit of u substitution on this. So in fact, both of these will start the same. So we're going to let u equal x cubed plus 5, which means that du is 3x squared times dx. So I'm missing one factor that I want. So again, we'll just use our idea of multiplying by 1. So if I multiply by 3 inside, I'll multiply by 1/3 outside. That way I've changed the look, but not the value. I've multiplied by 1. And you've been doing that since you've been building up fractions to add and subtract fractions with unlike denominators. The idea of multiplying by 1. Okay, and our bounds here are still from 1 to 5 on the x's. So here's where the two methods split off. So one option has us just putting in sort of placeholder endpoints of a and b. So this would be 1/3 integral from a to b, so just sort of dummy placeholders, mannequins standing in for the real ones. They're mathematical stunt doubles. They're not the real thing. They're just placeholders. So 3x squared times dx, that is a du. X cubed plus 5, that is a u. So hopefully you recognize that as a natural log. And we would evaluate from u equals a to u equals b. So we need to get back to our original x. So natural log of u, back substituting, is x cubed plus 5. And we're going from x equals 1 to x equals 5 again. So then this would be 1/3 we have 1/3 natural log of 5 cubed is 125 plus 5 is 130 minus natural log, absolute value of 1 cubed is 1, 1 and 5 is 6. So this would be 1/3 natural log of difference with the same base. We can turn it into a quotient, 130 over 6. Since that's a positive, I don't necessarily need the absolute value anymore. So 1/3 natural log of, we can do a little bit of reducing there. They have 2 in common, but not 3. So cut that in half, so that'd be 65 over 3. So that's one method of just putting in temporary placeholders. The other option, if you don't want to go back to the original variable, if you just want to finish it out in the variable u, is when we do this substitution, I'll try this in blue. When we do our let line, let u equal x cubed plus 5, and du is 3x squared times dx. One additional step is we use this first line to rewrite the bounds. So if x is equal to 1, u is worth 1 cubed plus 5, u is worth 6. If u is worth, if x is worth, x is worth 5, u is worth 5 cubed plus 1. Plus 5. I don't know where I got that plus 1. So $1.25 plus 5, $1.30. So then when we do our u substitution from here, we still would have had our 1/3 and our 3 here. But from that stage, we would have our 1/3 outside and turned our x equals 1 into u equals 6. Turn our x equals 5 into u equals 1/30. Still have our du over u. We would still get 1/3 natural log absolute value of u. But instead of dummy endpoints a and b, we have the values of 6 to 130 in u. So these are u equals 130, u equals 6. But notice our answer would still be the same. So 1/3 natural log absolute value of 130, that looks familiar, minus natural log absolute value of 6. And after that, it looks the same as the previous one. So you'll get the same answer whether you turn it back into an x or just move your endpoints into u as well. You'll get the same solution using either method. So next up, we'll try another one where we use substitution. We'll go from 0 to 3 of x squared root of 7 minus x quantity times dx. So here, hopefully you see the u that we're likely to use, 7 minus x. So du would be -1 times dx, or just opposite of dx. One other thing you may have spotted is that we have an x by itself, so we can use this guy to get an x by itself. So if u is 7 minus x, then x is 7 minus u. So just add x on both sides, subtract u on both sides. And let's see, this one, I'll show you both options again. So either one, we do need to do our little replacement. So integral from either a to b, or the other one will do a little bit more work. So x gets replaced with 7 minus u. 7 minus x is a u, so u to the 1/2, since it's under a square root, and dx is the opposite of du. So we can go ahead and just multiply this by the -1. So integral from a to b of u minus 7, u to the 1/2 times du. So that's the integral from a to b of u to the 3/2 minus 7u to the 1/2 quantity times du. So 3/2, add 1 to the exponent in the form of 2/2, and you get to 5/2. So we need a 2/5 there. And your minus 7, u to 1/2 is now u to the 3/2. So we'll need a 2/3 there. And all of this is going to be evaluated from a to b. So we want to do a little bit of cleanup and put our original x back into it. So we would have 2/5 times u is 7 minus x. The 5/2 minus 14/3, and then u again is 7 minus x, this time to the 3/2. And we're going from x is 0 to x is 3. So we'd have 2/5 So 7 minus 3 is 4. Square root of 4 is 2. 2 to the 5th is 32. Minus 14 thirds. 7 minus 3 is 4. Square root of 4 is 2. 2 cubed is 8. Then minus quantity 2/5. 7 minus 0 is 7. 7 is not a nice, neat, perfect square, so that one won't turn out nice and pretty. We'll just have a 7 to the 5/2. Minus 14 thirds times 7 to the 3/2. So we just clean up what we can. So a little plug-in and checking on the calculator. This part gives us a negative 368/15. And then just knock down those parentheses. So minus 2/5, 7 to the 5/2. And then plus 14 thirds, 7 to the 3/2 power. So that's as simplified as we can get that one. We can do a rough decimal approximation, but this would be our exact solution on this. If we went through and changed our endpoints, if you prefer that method, if x is equal to 0, u is equal to 7 minus 0, u is equal to 7. If x is equal to 3, u is equal to 7 minus 3, u is equal to 4. So your a, the 0 turned into a 7, and the b, your u, turned into a 4. So notice 7 minus the 3 gave us that 4. 7 minus the 0 gave us the 7. So notice that we would have gone bigger number to smaller number. That's okay. That would still have given us the same end result. So we could have just from here went from, if we used option 2, instead of our a and b, we would have been putting in our u equals 7 on our u equals 4. Okay, so I'm going to have you all try one of your author's problems. So let's see, just pick one of these. We'll do integral from 2 to 5, 1 over the square root of 6 minus t times dt. So see if you can do a little substitution on that one and find an area out of that. Okay, welcome back. Hopefully you picked out your u value as 6 minus t. So du is minus dt. And we'll just run through it. We'll kind of show a little bit of both options. So if you don't translate the 2 and the 5, you're going with just endpoints of a and b. I need a -1. I don't have it, so we'll multiply by -1 inside and outside. That way we're multiplying by 1. So this would be the opposite of the integral from a to b. -1 dt is du. 6 minus t is u, so u to the 1/2 downstairs. So that's the opposite of the integral from a to b of u to the -1/2 times du. So that's the opposite of u to the -1/2 add 1 to the exponent. Now we're at positive 1/2. Reciprocal of that is 2. And we're going from A to B. And then we put our original back in. So u is the same as 6 minus t. So this is -2 square root of 6 minus t evaluated from t is equal to 2 to t is equal to 5. So that would be -2 times the square root of 6 minus 5 is 1 minus square root of 6 minus 2 is 4. So -2 by 1 minus 2. That's -2 by -1. So exactly 2 square units. So nice, neat, and pretty. Sometimes they do turn out nice, neat, and pretty. So one other thing we can do with these is talk about the average value over a given interval. So the idea here is that if we think of turning some arbitrary curve, and I'll just draw a nice little sketch. So here's my endpoint A, here's my endpoint B. If I want the average value, I can think of turning that basically into a rectangle. So a rectangle, once I figure out the area of this, I can say, okay, well, this says the area is so many square units. Well, the area of a rectangle is just, remember, for a rectangle, length times width. Well, we know the width. If we know the area and the width, the length of this, the height basically, would be area divided by width. So we can use that same kind of idea and say, okay, well, if I know the total number of square units of this and I divide by how wide it is, that's on average how tall the function is, and that would be my average height. So let's look at an example. So let's say we have f of x is opposite of x squared minus 4x plus 11 and -3, 1. So we know this is a parabola, it's opening down, etc., etc. But I want to know what the average height is on this -3 to 1 interval. Well, our average height, the width, is 4 units. 1 minus a -3. And instead of dividing by it, we'll multiply by the reciprocal, since that's the same thing. So our average height, there's our width. Take the area. How do I find the area? Integral. We use the integral to find the area. So it's -3 to +1 of this opposite of x squared minus 4x plus 11 times dx. So my average height, average value over this interval, is going to be 1/4 of the area. So how do I find the area? X squared turns into x cubed. So I need a -1/3 out here. That way -1/3 times 3 gives me the -1. X to the first turns into an x squared. I need a -2 there. -2 by 2 gives me the -4 there. Antiderivative of 11 is 11x, and we're going from x is -3 to x is +1. So average value, average height, it's going to be 1/4 of, plugging in the 1, -1/3 minus 2 plus 11 minus what happens with the -3. So -1/3 times -27, two negatives make it a positive, and 27/3 is 9. -3 by -3 is +9. -2 by 9 is -18. And 11 by -3, -33. Average value or average height. So it's going to be 1/4 of, let's see, so we have -1/3 minus 6/3, or we'll turn that into a 9. So 9 is 27/3. And then we have, let's see, -9 minus 33 is -42. So our average, so that's 26, 1/4 of 26/3 plus 42 is 126/3. So 1/4 of a third is a 12th, and let's see, 152/12. And let's see, then we can do a little simplifying there. So a common factor of 4. So 4 will go to 15 3 times, 3 left over. 4 will go to 32 8 times. And 4 will go to 12 3 times. So that is, let's see, 12 will get us to 36 with 2 left over. 12 2/3. So an average height of 12 2/3 over the interval -3 to +1. Change the interval, you could change the average height. I'll have you all try one more. Another one of your authors. Average height, average value. Function g of t, 6t squared minus 2t. T is on the closed interval -2 to 3. Okay, welcome back. So this one, hopefully you didn't need any substitution. So our average value, 1 divided by the width of the interval from -2 to 3 is 5 units. Integral from -2 to +3 of 6t squared minus 2t quantity times dt. So our average value, a fifth of t squared is now t cubed. We're doing the antiderivative. 3 by 2 would get me to the 6 that I had there. T to the first is now t squared, and it looks like that's already taken care of then. And we're looking from -2 to +3, so our average value is a fifth of that integral. So 3 cubed, 27 by 2, 54, minus 9, minus plugging in the -2. We have an odd number of negatives, so that's -2 to the 4th, 16, and minus +4. So our average value, a fifth of, so 54 minus 9, so that's 45. Minus a -20 is +20. So our average value is a fifth of 65, so 13 is our average height. So over that interval, it's not saying that it's always at that height. It's saying that on average, that's the height of the function. It's the average output. So in 5.5, if you're doing the textbook ones, 9 to 61, every other odd, 71 and 75. If you're looking for the electronic homework, let me know and I'll post an equivalent electronic version. If you have any questions, please get in touch. Otherwise, I'll see you next time. Stay safe out there.